Assalamualaikum warahmatullahi wabarakatuh. So welcome back to my video. So we will continue with part number 3 of chapter 4 on the three-phase complex power calculation. So we have the sub-chapter number 8 on the power consumed by three-phase load. So just consider a three-phase load, a star-connected three-phase load as shown in the figure below. So by the conservation of Niji principle, so the total power consumed by a three-phase load is given by the sum of the powers in each phase. Thus, we can simply write that the total number of power, the real power, so is actually VRN IR cos theta R. This is for phase R, alright, the red phase. So similarly for Y phase, we do have VYN IY as well as cos theta Y. So this is for the second phase. Okay, and then the third phase is VBN IB as well as theta B. So this is the third phase, or the blue phase. So by totaling up these three quantities, okay, we can simply get or obtain the total number of power, where VRN, VYN, and all the quantities here are phase quantities. All right, so this is one of the keyword, or one of the very good uh, tips for you before you proceed with your analysis. So remember, so everything must be in phase quantity. Okay. So then if the load is balanced, then VRN, this is equal to VYN, VBN, V phase, right? So this is just an assumption. So we have seen this in the earlier topic, all right, of this course. So IR, so this is equal to IY, IB, I phase, and then theta R, right? So this is equal to theta Y, theta B, so this is equal to theta. So where ZR, so the impedance for red phase, so this is equal to Z theta R, so as well as Y impedance plus blue impedance. Okay, so they are all in phase quantity. So therefore the total power, so P equal to VRN, okay, IR, so VYN, IY as well as VBN. So since these three VRN, VYN, right, so as well as VBN is actually V phase, so we can simply say that this is all equal. So we just multiply VPH by 3. Okay, so we got over here VPH. Similarly, so happen to IR for I quantity. So I R plus IY, okay, over here plus IB. Okay, so this is actually PH or phase current multiplied by 3, right? So that's why we can we see this IPH over here, the phase current multiplied by 3 and cos theta, right? So again, no difference between theta R, theta Y, and theta B, as we have defined that all the theta here are identical, right, to theta. So for a balanced star connected load, so remember V phase equal to VL over square root 3, and equal IL to I phase. So therefore, P equal to 3 phase I phase cos theta from here. So we can simply convert into this new equation. So just substitute this value into here as well as this one, and then we can simply get 3 multiplied by 1 over square root 3 VL IL cos theta. And this gives us a more simplified equation where P equal to square root 3 VL IL cos theta, and this is a very useful equation once you come to the system analysis. All right. So what happened if we do have a delta connection? Okay. So data connected and of course balance. So VL equal to VVH or line voltage equal to phase voltage, and line currents equal to square root 3 phase current. So from which it follows that total power P equal to square root 3 VLIL cos theta. This is what we have derived early in the previous page. So thus for either method of connection, okay, either method of connection, whether it is delta or Y or star connection. So the total power in the three-phase balance load is given by P equal to V 2 square root 3 VLIL cos theta. So this means that providing we know the line current and phase-to-phase line voltage and the impedance, we can always calculate the total power consumed by the balance load without having to know how it is connected. So regardless the configuration of the system, so is it either delta or star? So this equation is all the time applicable. All right, so we can use this equation regardless the configuration of the system. Okay, start or delta. So then similarly, if you come to Q, all right, the reactive power consumed by three-phase load. So the sum of reactive power consumed by each phase, that is Q equal to QR for red phase, QY for yellow phase, and QB for blue phase, where QR equal to VR IR sine theta R, right? QY equal to VYIY sine theta Y, as well as QB equal to VBIV sine theta T. But this is again a phase quantity. So if the load is star connected and balanced, then V phase equal to VL over square root 3 and IL equal to I phase. Okay, so remember this is a star connected load. So thus Q equal to 3Q phase equal to 3 V phase I phase sine theta phase, and again, so you just need to substitute this value into here, all right, as well as this equation into here, and we get again Q equal to 3 multiplied by 1 over square root 3 VLIL sine theta, and we can simplify the equation into this, right? So we have seen the earlier equation for P, and now it comes to new equation for Q. So instead of cos for P, now we have sine theta for Q. Okay, if you refer back to the previous slide or the previous page, we can see P equal to square root 3 VLIL cos theta, and what makes these two equations different is only the sine and the cos. All right. Again, I repeat, P for Q cos theta for P and sine theta for Q. All right. And then since complex power S equal to P plus JQ, so this is real power, and this is for Q power, reactive power. So then apparent power consumed by a balanced three-phase load is given by the expression S equal to square root P square plus Q square. Right? So just substitute this P and this Q into this P and into this Q, square root 3 VLIL cos theta square plus square root 3 VLIL sine theta square. Square everything here in this first bracket and square everything here in the second bracket. So you might get this relationship. Okay. Then from here, you may factorize into 3 VL or V line square, I line square in bracket cos square theta plus sine theta square. So from these rules, so we may know that cos theta square plus sine theta square is equal to 1. This is actually 1. And then again, we can simplify our complex power S equal to square root 3 VL square I L square, and therefore S is actually equal to square root 3 VLI IL. All right, so this is somehow the derivation on how we can obtain the equation or the relationship of power complex in terms of line voltage and line current. Okay. Work example, so 3 analytical coils, each having a resistance of 20 ohm and an inductance of 0.5 Henry. So are connected in star to a three-phase supply of 400 volt, 50 Hz frequency. So you calculate first the line current. So the total active power P. Okay, so let me write the symbol. So the line current is IL over here. So the total reactive power, this is a Q, and then the parent power absorbed by the load. All right. So this is how the configure or the circuit looks like. So we have the line to line of voltage, which is level at 400 volt. We do have the second phase, second line voltage to line, line to line voltage, which is another 400 volt, as well as the third phase. Okay, so this is for phase voltage. So we do have, for example, here the N node or on end point, and then let's say we have R over here, and this is obviously our V R N, okay, which is equal to 400 over square root 3. Okay, so this is the impedance value for each phase R, Y, and B. Okay, given by 220 ohms plus J 0.5 omega J omega L, or 0.5 H. So first of all, calculate the impedance of the coil. So given R equal to the resistance value 20 ohm, and then the inductance value 0.5 H. So therefore XP equal to 2 pi, right? So F L. So this is given in the equation, which is 50 Hz, and this is also provided in the equation, which is 0.5 Henry. So solving this, so we obtain 157 ohm. So coil impedance is, all right, ZPH, or the phase impedance, equal to RP plus JX XP. So this is equal to RP square plus XP square, and square root everything here. So this is the angle where theta equal to arctangent XP over RP. So just substitute the value of 157 here, and RP is 20 ohm over here. All right. You may also find from rectangular. You may transform from rectangular value to a polar value. Okay. So we have plus J over here is, for example, this is L. So we can XL over here. So we have 20 plus J157 ohm. Okay. All right. Then simply transform all this into polar. Okay. So therefore, for the phase impedance, we have 158 at the angle of 83 degree. So since the load is balanced, so V phase equal to 400 over square root 2 and give us 231 watts. So current taken by the phase load, I phase equal to I line, and this is equal to V phase. This is according to Ohm's law, V over Z. Okay, you take the value of 231, so divided by 158 for the magnitude of impedance, phase impedance. Okay. Then finally we get the line current, or the phase current, is equal to 1.46 ampere. So total power absorbed by the load is P equal to square root 3 VLIS cos theta. So where cos theta equal to cos 83 degrees. So we obtain here from here. Right, this is the value of 83 degree from the impedance value. So put it here, okay, cos theta, and you get the value of 0.1264. Right, so therefore P equal to square root 3. This is P L, the line voltage. So this is IL, the phase current we just calculated, which is equal to IL, obviously. And then this is cos theta. So the value we just calculate. So this is giving 128 watt. So total reactive power absorbed by the load, square root 3 VL sine theta again. So take the value of theta, put it here, which is 83 degrees. So this is I line 1.46. So this is V line, which is 400. Again, let me write it here. Okay, I line, so 1004 var is the total reactive power absorbed by the load. Okay, and then total apparent power absorbed by the load. So S equal to square root 3 VLIL. So again, set the value of VL and IL. So you get 1012 volt amperes. Or there is another option, or alternatively from power triangle for inductive load. So we get, so this is S, this is P, this is J. So this is JQ. So just substitute the value of P and Q. So you get the value of S, the total power absorbed by the load. Of course, you need to refresh on this trigonometry chapter. Then for example number 2, so 3 identical coils, each having a resistance, again the same value of the impedance, but this time around it is, or they are connected in delta configuration. So to a 3-phase supply of 400 volt 50 hertz frequency. So calculate the, again, line current. So the total active power, so the total reactive power, as well as apparent power absorbed by the load. So again, so we have our supply over here, okay, the three-phase supply over here, which is 400 volt, supplying to a data connected system or data connected load with 20 ohm resistor. Resistance plus 0.5 Henry inductance. Okay. Solution first, the coil impedance. So this is what we have seen earlier. So this is about the same steps. So phase, the impedance phase, so 158 80 degree ohm. So since the load is balanced, so V phase equal to V line equal to 400 volt. This is for, remember, this is for delta. So once you come to load phase, so you must remember that I phase equal to V phase over Z phase, or phase impedance, phase, sorry. So this is again Ohm's law. So just substitute the value of 400 as well as the ZPH over here, the phase impedance. Then this is equal to 2.53 ampere. So this is over here. Okay, and then in order to calculate the line current, so you need to multiply by square root 3. All right. So this is giving 4.38 ampere. So for the line current. So what about the total power absorbed by the load? So again, remember this equation. So P equal to square root 3 VLIL cos theta. So again, the 83 degree here is taken from the angle of Z. All right. So the impedance is value. So cos 83, this is 1.122. So therefore, the total power absorbed by the load is, again, square root 3 to VL over here, this is 400 IL, so we just calculated earlier, so we do have the new cos theta, which is 0.122. So the total power absorbed by the load is 369.82 watt. So total reactive power absorbed by the load, so remember the equation, so sin theta, the same value of PL, the same value of IL, but this time we have sign operation over here. Okay, then the final value of Q is T01 to bar. So total apparent power absorbed by the load S equal to square root 3 VLIL. So just substitute the value of V as well as the IL. So we get the value, parent power value is equal to 3035 volt amperes. And then alternatively, so remember this triangle, power triangle, or the trigonometry. So S equal to square root P square plus Q square. So again, take the value of P from here, this P and this Q, into this P and this Q, so we get as the parent power absorbed by the load is equal to 3035 volt amperes. So exercise, so a three-phase star connected balance. So this is what we have seen earlier. It's about the same thing, but you have to play around with the new value of phase impedance, okay, as well as the three-phase supply. Okay, so you can try it yourself. The second exercise, similarly, so it's given a different value of resistance as well as the inductance with balanced data load. All right, so find the line current, the total active power, reactive power, as well as the apparent power absorbed by the load. All right. So until now, thank you very much for your time. Thank you very much for watching. So we will continue the end part of our chapter in the next coming video. Again, thank you very much.